come to understand that maths is a lot of fun. All through high school, I used to think that maths is all about numbers. But then I was introduced to a whole new dimension of mathematics when I got to university, and I realized that maths actually included a lot of theory. You have a whole page when you're explaining, or rather proving stuff that you thought was always so. For example, I can always remember the very first time I was asked to prove whether really 1 + 1 was 2, why I thought it was that. But I thought that because it is. But when you really get to learn more about mathematics, you realize that there's more to it, more than what we know, what you're taught throughout the first stages of primary school and maybe high school. You never really get to understand mathematics. And it adds substance to what you know already, because you really get to understand why what you did or what you always assumed to be true is true. You can really get to understand why when I differentiate, I lower down the power and reduce the power of the expression by 1. You can really see where it's all going. And you can really get to see why certain limits do not exist, or why certain differentials at certain points do not exist. And I think it's a whole lot of fun. At some point, you were told that 2 - 3 was impossible. You couldn't solve it. I know that I used to chant a whole lot. If somebody was to ask me when I was in grade 3 or maybe grade 4, what is 2 - 3, I'll tell them it can't. It's not possible. But then, as I progressed, when I got to high school, I realized, oh, there's actually the rule number line extends. 2 - 3 is equal to -1. Then you progress further and to realize that the square root of a negative number could be given a value. Then as you progress further, you realize that you can actually prove that 1 is greater than 0 from the definition and the precise definition that we have for 0 and 1. We're going to be talking about, say for example, we want to have an expression like, say now we add another variable, z. We now have something that looks like this. We want to talk about a case where x or y or z. But how do we express this without any confusion, without any ambiguity? We're going to now introduce brackets in all these expressions, where we have x or y in one bracket, or z. So now, if we now have 3 variables, x, y, and z, or rather, 3 expressions represented by x, y, and z, and we want to form a logical statement that includes the logical expression or and, or whichever one, how then do we derive a truth table for these expressions? It's very easy. We introduce brackets. That way, you first have to determine the truth, the truth table for this, and then for that, and you can easily have an overall statement. So, say for example, in this case, we have x, y, z, then we have x or y, and then now we're going to say, let's call this expression star. So we're going to have cases where true, 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 false, true, false, these are at least 6 of the 8 expressions that we can form of the different states that x and y can have. But just to show you how you can derive the overall truth table for such a long expression, we now say x or y. When you're dealing with x or y in this case, you can ignore what the state of z is, because all we want to find out is what is happening here. So we now use what we know. If x is true, y is true, then this is true. Because remember, all we need is for one of the 2 to be true. True and true, it remains true. True and false, it remains true. False and false, it becomes false. And then false and true, we have a true. False and true, we have a true. Now, for this, now consider the truth table of all of this, or Z. So therefore we are now saying this or that, and now we include Z, but we now ignore what is happening here. We now have true and true, that remains a true. Sorry, true or true, that remains a true. False or true, that's still a true. False or true, still true. False or false, that becomes a false. False and true, that's a true. True and true, that's a true. So can you see how easy it is for you to come up with a truth table for howsoever long the expression can be? Even if you think of putting 10 or even more of these logical connectives, you can still find the truth table of any of those expressions by simply putting brackets where you need to have them. So now, we have managed to derive the truth tables for large expressions. We already know when two expressions that have an and or that have an or, when are they true and when are they false. Now I want us to do something more. Let's think about an expression that can involve both of them. So now say we have A, B, C. They are joined by A and B. Put brackets around it. So what do? So I hope you have your pen and paper ready. Let's do this together. So now, you're going to go all the way to stop. True, true, true. One more. What am I leaving behind? So now, we know that we need 8 of these. So what's the last one? Oh, yeah. Now, we have 4 of the truths, so we need 4 of the false. So here we know we need a false. Okay, there we have 1, 2, 3, 4, so we know we need another false here. Then here we have 1, 2, 3, and 4 of these are in, so true there. There we have all the 8 different states that A, B, and C can take. So now, we now have a logical connective and, in this case. So, A and B, remember what I said when we did the previous example. You ignore what is happening in C and you just consider A and B alone. So true and true, that is true. True and true, that is true again. True and false, remember this is different from or, and with the condition that we have when we use the logical connective and is that both statements or both expressions have to be true. In this case, we fail to meet the condition. Therefore, that is false. False and false. False and true is false. False and true is false again. True and false is false. False and false is false. For the expression star, we now consider what is happening here in the column C. But we have to remember now what the logical connective between them is. The logical connective is or. And what did we find out when we were dealing with the truth table for or? One of them has to be true. So true and true. So this is basically a truth table for the long expression that we have that even has a mixture of the logical connectives and an or. That was easy, right? Good.